All right, class. So we have to start with induction. So only induction is left from your electromagnetic induction. This lesson will be over. Not today, definitely in the next class. By Thursday, we'll end this lesson. Walaikum assalam, Fahad. Test on Thursday. Why? You're not prepared with the test. Any specific issue, Fahad? I'll postpone it, but let me know the exact reason for this. See, induction, let's study. Induction means what? Induction means generation of EMF, but because of presence of change of flux that you have. See, self-induction is what? Self-induction you have, and you have mutual induction. Okay, you're not fully prepared for the test. All right, then I'll take the test on Thursday, but Thursday is it? Right? Thursday means Thursday. Thursday I'll take your test. So 1 hour test you will have on magnetics, right? Now, self-induction means what? Self-induction, it's a phenomena of property of induced EMF in a coil. See, definitions and everything I've already written for you. Let's understand the meaning of it. There's a coil, fine? Magnetic flux is changing in this coil. There's a change in the magnetic flux in this coil. So what is happening? Because of change in the current, magnetic flux, EMF is getting introduced in this, induced in this. So this EMF, this induced EMF is because of induction of what? Change in the flux within the same coil. That's why you say it as self-induction. Self-induction kya hua? See, if there's a change in current, change in voltage, or because of any of the factor that changes your flux. So your flux gets changed, there will be an induced EMF present. EMF will get induced obviously in this. So if you have induced EMF in this, what will happen? There will be, you call this that this EMF has been induced. We have been studying this induced EMF. It's just that this induction we are referring to as self-induction specifically because the change in the change in the flux is occurring in the same coil and the induced EMF is getting induced in the same coil. You do not have more than a single coil or any device for it. Fine. So I've written the definition as well. Yes, self-induction is a phenomenon of production of induced EMF in a coil when a changing current passes through it. Fine. When a changing current passes through it. All right. Now, see, there are two circuits which you can see. In one of the circuits switch is closed, in the other circuit switch is open. Here what is happening? Current is increasing because you have closed the switch. As you close the switch, initially the current will rise from zero value to a very higher or a maximum value. So what will happen when once you close the switch, current gets higher, current increases, so the flux increases. As the flux increases, your current increases, there is an induced EMF. Other possibility, induced EMF where? In this coil only. Flux is increasing, current is increasing in this coil. So here what is happening? Here you have opened the switch. When you open the switch, once you open the switch in here, current will decrease from a higher value, the maximum value that it has reached. It will decrease, it will drop down, the value will decrease. So the magnetic flux that is linked, that will also decrease. An induced EMF will be generated, induced current will be generated. But where is this happening? This is occurring in the same coil. So these two circuits depict your phenomena of self-induction easily. Self-induction. induction within the same coil. It is inducing itself only. There is no presence of other coil that it will induce. It is inducing itself only. Current increases, flux increases, or current decreases, flux decreases. Anyway, either of these happen, your induced current is generated, your induced EMF is generated. Got it? Yes, exactly, Far. To produce something. Induce means to produce. You are inducing something. You are producing something. Like here we are producing EMF. So that's why, because see, EMF is there in the circuit, but we have intentionally produced this EMF. No, because by changing or altering the magnetic field and so the flux and current. So that's why we say that is induced current and that is induced EMF, because that is not naturally present within the battery and the circuit that you have as direct current. Here the current has been induced specifically. So this is the difference between the normal current that we say and when we specify induced current specifically in your circuits. Fine. So these two circuits are there which show you the exact procedure of self-induction. Now see, regarding the formula and derivation, no such derivation is there. Derivation is not there for self-induction. But remember what happened in both the circuits that I have just discussed. When current increased, flux increased. When current decreased, flux decreased. Can any of you tell me the relation between current and flux? Directly proportional, inversely proportional. What do you think? By looking at the content that I told you just now. Flux increased, current increased, flux decreased, current decreased.
And directly proportional.
Directly proportional, obviously, correct, Fahad. So here your flux is directly proportional to current. How do we remove the proportionality sign? We put an equal to with a constant. Here the constant is L, that is coefficient of self-induction. Phi is what? This is your magnetic flux. This is coefficient of self-induction, coefficient of self-induction, or we simply say self-inductance. This will be used in alternating current also. Please pay attention to L. This will be used. So this is what? This is self-inductance. This is self-inductance, right? So coefficient of self-induction you have on one side and on the other side you have self-inductance. Both the name give rise to the same quantity, that is L. And I is what? I is the current. Phi is equal to Ln. Now EMF was equal to what? According to Faraday's laws of EMI, Faraday's laws of EMI says your EMF, this is directly proportional to rate of flow of magnetic flux. Remember we did E is equal to minus d phi by dt, and minus sign represented that Lenz's law. So if E is equal to minus d phi over dt, phi is equal to value of phi, so this becomes d Li over dt. This is a constant right now. Only you have studied that it's a coefficient of self-induction or self-inductance, and it's a constant term. So it will come out minus L differentiation of di over dt. Fine. This is EMF. Minus L di over dt. Now, if you want to say what is L, L from here will be what? EMF into dt by di, or just a second. We can write this, see. We can write the value of L from here as EMF divided by this whole term. EMF divided by di over dt. So if this is 1 volt and this is 1 ampere per 1 second, so that will give you self-inductance. So how can you define self-inductance? See, I have written it. Self-inductance is numerically equal to the magnetic flux when a unit current flows through it. Unit current flows through it means 1 ampere flows through it per second, actually flows through it in 1 second to complete it. So self-inductance is numerically equal to the magnetic flux when a unit current flows through it. Fine, that is your coefficient of self-inductance. Unit also you have it for self-inductance. The phi you already know that's Weber. For this current you already know it's ampere. So new quantity is L only. So SI unit of this is Henry by the symbol H we write. Fine. SI unit is Henry. You can even calculate its dimensions also. Dimensions you can simply calculate if by putting in this formula L is equal to voltage's dimension you can write divided by dimension of current inverse to time. Like this you can find out. Dimension is not asked, but yes, unit you have to remember. 1 Henry also you can define 1 Henry as what? L is EMF by di over dt. That means voltage by ampere per second. So 1 Henry is 1 volt per 1 ampere by seconds. Right? So this way you can define 1 Henry as well. If question asked, 1 volt is there and 1 ampere per second is there. No. It's not no specific value for constant. It's not a universal constant. It is a constant term. It does not depend on anything, but its value is variable. L will be provided to you in the question. Do not worry about L. But do remember L because in your alternating current, L will be used. You should have the knowledge. Capacitance will also come back. Resistance from current electricity will also come back, and L from EMI will come back. Capacitance from potential lesson, electric potential and capacitance. Resistance from current electricity, and L from EMI and self inductance. That's why I'm saying pay attention to this. Okay, note it down first. Note down the self induction. But Fahad, one more thing. Since your chapter will then get ended today, so next Tuesday will be your test of EMI because it's a short chapter, so I'll not divide it into parts. When do you want the test of EMI then? Because if you're saying to take the test of magnetics on Thursday, then EMI का कब होगा? Will you be able to prepare by Tuesday?
Yes, ma'am, it is fine for me.
Oh. So give the test on Thursday. See Friday, Saturday, Sunday, Monday. This is a short lesson. A very short lesson is there. Just in case if it is not suitable for any of you, let me know. I'll postpone the test then. But by far, it's EMI's test on next Tuesday. Because this chapter will be over this week. So next week, you should give a complete test of it. See, 3 topics are only there in this. One is that starting portion, which includes your Faraday's laws of EMI, E is equal to minus d phi over dt, that content, fine. Then second part you have Lenz law and motional EMF. Lenz law we did that opposes the cause and motional EMF is BLB. And last part is induction. So I think you all will be able to do. No, Sal, you are not having the test today. I have postponed the test to Thursday. Thursday to carry it. 20th, no, so 22nd. 22nd you have the test. Fine, Sal.
Okay, ma'am.
C class. Solenoid, do you remember? Solenoid we have done. What was the formula of magnetic field due to a long solenoid? You were supposed to have your test today. Formula, at least you all must be remembering it. Formula of the solenoid. Darshan, Fahad, formula of magnetic field for solenoid. Priya, Priyadarshini. Sahal, nobody remembers the formula. Fahad, you're answering something. B is equal to mu naught Ni. That is the formula of magnetic field for a solenoid. Mu naught Ni. Now see, flux is what? Flux is B dot A. So if you find out the flux, magnetic field is mu naught Ni and area will be A. If you wish, you can substitute this area also as pi r square, area of the radius of the circle. Now we are trying to find out if a long solenoid is kept. Then current will be induced in this. Magnetic field will also change. Magnetic flux will also get induced. So EMF will be induced in it. So self-induction will occur because it's an ordinary coil actually. So phi is equal to mu naught Nia. Now see, magnetic flux linked with entire solenoid. This is for a single turn. Mu naught Ni is for just one. If I have to find out magnetic flux that is linked with the entire solenoid, so if I multiply flux linked with each turn, flux linked with each turn is what? Mu naught Nia. Why? If I multiply it by the number of turns that are present, that will give me the complete. So number of turns are what? Number of turns are small n into L. How I have written this? See, small n is number of turns per unit length. From here, number of turns will be equal to n into L. So this becomes mu naught Nia into Nn. So this becomes mu naught N square IAL. This is flux. Right now we have studied flux is also equal to Li. Now compare both of these. Phi is equal to mu naught N square IAL with phi is equal to Li. So Li becomes equal. This is a derivation. This is a derivation. Mu naught N square IAL. Current gets cancelled. Self-inductance formula becomes mu naught N square A into N. Remember, for solenoid, we have specified n is equal to number of turns per unit length. So wherever this is asked, please mention this. Fine. Note this down, then we'll do a question on this. Noted. Pi r square is the area of the circular section, cross section of the solenoid, pi r square. See, the question says a 12-volt battery is connected to a 6 ohm 10 Henry coil through a switch, drives a constant current through the circuit. The switch is suddenly opened. If it takes 1 millisecond to open the switch, find the average EMF induced in the coil. So voltage or EMF that is given is 10 volt, inductance is given as 10 Henry, the resistance is given as 6 ohm, and time is given as 1 millisecond, that is 10 to the power minus 2 second. See, using V is equal to IR, you can find out the current first. Current will be V by R. So V is 12, current is 6, that is 2 amperes. Now EMF, induced EMF will be what? L minus L minus L di over dt. minus L di over dt. This becomes minus 10 into divided by 10 to the power minus. So EMF will be minus 2 into 10 to the power 4. Right? Note it down.
Ma'am, is that minus 2 into 10 raised to the power 2, right?
Minus 10 into 10 to the power 4.
In the
See,
answer.
uh, answer no here, no? 10 to the power 4. 10 to the power 4. See, 10 to the power 3 into 10 to the power 10, that will be 10 to the power 4. See, let's take a break of 5 minutes. Revise self-induction. If you have any doubts, you can ask me. Then we'll start with mutual induction. mutual induction means what? Mutual induction means if the current increases or decreases in one coil, flux changes in this coil. Okay, all of you not back. They will join. One has already joined. But the EMF has been induced in another coil. That means mutual induction. Self-force, all these phenomena were occurring within the same. This is mutual induction. Mutual induction means more than a single coil is required. In the first coil, either current will increase or decrease. According to that, flux will increase or decrease, but you will have an induced EMF. And as soon as induced EMF will be there, induced current will be there, and this galvanometer will show deflection in either of the directions. Fine. So it's the phenomena of production of induced EMF in one coil due to change of current in the neighboring coil. So here also flux is directly proportional to current, but the constant term that you get over here, this is M, mutual induction. So coefficient of mutual induction. So phi is again it's the magnetic flux. Okay, one more thing. This we'll see it in detail when we do transformers in AC. But this coil where current is changing and flux is getting changed, this is known as the primary coil. And the other coil where this EMF has been induced is the secondary coil. So phi is equal to, so here phi is what? Magnetic flux in in primary coil. And current is induced current in secondary coil. And M here it will be coefficient of mutual induction. Or you can even say mutual inductance. Fine. So phi is equal to M. Again, if you will calculate EMF, that will be E is equal to minus d phi over dt. Put the value of phi, you will get minus d mi over dt. M will be the constant, so this will become E is equal to minus M di over dt. Right? This is the induced EMF formula in terms of mutual induction. SI unit will still be 1 Henry only. SI unit, this will be still 1 Henry. Henry is the unit. SI unit of this mutual induction, this is 1 Henry only, the SI unit of it. Fine. So even M, if you want to write M, you can write it as EMF divided by di over dt. So rest of the things that we have studied for self-induction, it will be valid. So note it down, then we'll do for two solenoids if you have, same thing. Question C, one question we have already done on self-induction. That type of question comes. For mutual induction, we will see. I'll share a question with you. But usually formula-based questions are asked, and to define mutual induction can be asked, or to define self-induction can be asked. Otherwise, to specify what is 1 Henry, it can be asked. So all these things that we have discussed, this way question can be asked.
Ma'am, the resistor will be placed outside the solenoid.
See, yes, sir. That resistor is rheostat actually that has been connected. It is just to vary the current, because when we'll vary the current, the flux will get vary, and so on, the induced EMF will be generated. So just in order to vary our current, we have a variable current. We have, because we want direct current only. So that's why we have put a rheostat. Yes, yes. Di is the change in current and dt is the change in time. So that's why we say rate of change of current, di over dt. See, two long solenoids are there because in mutual induction, two devices are at least used. So let's say we have one solenoid. Radius
Ma'am,
of the
is this a derivation?
I1. Yes, Fahad?
Is this a derivation?
Yes, yes, this is a derivation. The way we had the derivation for mutual self-inductance of a long solenoid. So here, this is also a derivation. And current that is flowing through here, this is I1. Now, had it been the case of only self-inductance, we would have just used this and this coil would have been sufficient. Now, we are taking one more coil. So radius of the second coil is R2 and the current that is flowing through this is I2. Now, current will change in one, EMF will get induced in the other. That is what is the whole phenomena of mutual induction. So, R1 is radius of coil 1, R2 is radius of coil 2, I1 is current of coil 1, I2 is current on coil 2, and L is the length of the coils. And both the coils have the same length. Both the coils have the same length. So, when you draw it with the same. And number of turns n1 for the first and n2 for the second. So n1 and n2 number of turns are present. Now magnetic field in the second solenoid if I calculate. See, magnetic field's formula is what? Mu naught Ni. So here also it will be mu naught Ni. But current in this, we are calculating magnetic field for the second wire. This is coil 2. So it will be N2 I2. Now N2 will be what? Number of turns in the second coil per unit length. That is right. No, number of turns per unit length is written like this. This is what N2 is equal to capital N2 by N. Now write down the value of phi. Phi will be what? Mu naught N2 I2. Area you will choose as pi R1 square. Find mu naught N2 I pi R1 square. We write no flux as what? B dot A. So magnetic field you already have, area you already know. Even you can write it in terms of this also. So that becomes mu naught N2 I pi R1 square divided by L. Fine. Now mutual induction is what? Mutual induction. This phi is equal to Mi this time. Instead of Li, this is Mi. So mutual induction of the second coil with respect to the first coil with respect to the first one will be phi1 divided by I2. See, understand this statement. Phi is equal to Mi. I am calculating mutual induction in the first coil. It means cause is the first coil. But where is the change in current occurring in the second coil? So that's why I have written M12 is equal to phi 1 by I2. Had it been M21, I would have written phi 2 divided by I1 like this. Now for M21, if I put the value of phi 2, mu naught N2, how much did I, what was the amount that I got? Mu naught N2 I pi R1 square L. I pi R1 square by L. This is what I'll get. Fine. U naught into I pi R square L 1 by L. This will be the formula of mutual induction. Similarly, if you want to write it for M12, this will be the same. See, derivation will be the same. For M12, this will be phi, M12 is phi 1 by I2 and M21 is phi 2 divided by I1. In both the cases, what will happen? This is your phi divided by I1. Current gets cancelled. Ultimately, you're left with M21 is equal to mu naught N2 by R1 square by L. And this is valid for both of it. Because the current will ultimately be cancelled and rest of the things will be the same. M21, see, M21 will be equal to M12, which will be, we can write it as M only. So mu naught N1 N2 A by L, or you can write it as mu naught N1 N2 in A into L, or you can write it as pi R square, pi R1 square L also. These are just a different forms that we have. See here what we'll do. When we'll multiply, how this N2 and N1 both are written together, it's just that we have multiplied it by N1 as well to get the number of turns that are present. Fine, number of turns in the first coil, we cannot ignore that. So that's why you have N1 also along. So mu naught N1 N2 A divided by L, mu naught N2 N1 A into L. This is volume. And mu naught N1 N2 area. This is area that I have expanded. Fine. And then you have one more term, coefficient of coupling. See, coefficient of coupling is just a constant term. This is M divided by under root L1 into L. If two coils are given, so this is the mutual inductance of both the coils. L2 is the self-inductance of second coil and L1 is the self-inductance of coil 1. Let me repeat it in brief, then our question we'll do and then you people can leave this, we'll complete off the lesson. Mutual induction is what? Mutual induction is induction between two coils. Now see, two coils are there having their respective diameters. Here what is happening? 1, 2 can be confusing. See, one is generating, other one is having the effect. So if magnetic field is getting changed on the second one, then you can see the effect on the other one. Got it? One induces it, other one gets induced. What about B1? B1C. B1 will come if we talk about here. We have calculated M12, so we required B2. If you were calculating M21, no, opposite to it, then you would have used B1 instead of B2. If it's just the opposite derivation of it, then we would have used B1. Got it, Fahad? Got your doubt? What you're asking?
Like the formula is same as of B2.
Yes, but that time B1 will be equal to mu naught N1 I1.
Okay. Got
Okay.
it.
You can calculate for any one of it. In your derivation, you can do for M12 only. You can just mention at the end whatever I have written. The rest of the things are same. We have not divided I in both numerator and denominator. It's this formula. One formula I am getting as value of phi as mu naught n2 I pi r1 square L. You can multiply this also by n1 over here. Fine. And the other formula I'm getting is phi is equal to mi. If you use this formula and this formula, then your current will automatically get cancelled. The way in self-induction it got cancelled, similar here also it will get cancelled. See, this question says what a solenoid of length 50 centimeters with 20 turns per centimeter. 20 turns per centimeter. Area of cross section 40 centimeters square. The second length will be the same. Area A2 is 25 centimeters square and N2 is 25 turns per centimeter. See, two areas are given. We have to consider only one area. Formula was what? Formula for mutual inductance of the system was mu naught N1, N2, A divided by L. So which area should we choose? See, if the coil is, this is 40 centimeter. Fine, this area is 40 centimeter. And this area is 25 centimeter. So do you see this fact that the current is occurring in the combined path only? There is no current here. So you will choose the shorter area because through the shorter area, whole current will flow. But if you choose the larger area, what will happen? This part will be left. So we'll choose here it as A2 because this is smaller. Got it? Why smaller? Suppose you have two rings with you. One is larger, one is smaller. And you're passing fluid through it. So what will happen? If you take that smaller diameter first, then only the smaller diameter will get completely used. Otherwise, if you use this, this space will be left emptied. That's why we use this, because this becomes a common space, this one. So m is what? Mu naught 4 pi into 10 to the power minus 7. N1 20, N2 25, A2 25 divided by length is 50. So this is 1, this is 2, 2 into 10. So this will come out to be pi into 10 to the power something. Yes, yes, Fahad. Current passes through the smaller area of cross section. See, this is, let's say this is 40 centimeters square and this is 25 centimeters square. If you have to find out the mutual induction, if you have to choose the common area by which the current will definitely pass. If you choose the whole part, current will not pass. If you choose just this part, from here, this hole will be covered only. That's why we write the area as A2. So you can solve this and write this. M will be what? 4 into 25 is 100. So pi into 10 to the power 2, pi into 10 to the power 2 into 10 into 10 to the power minus 7. So this is 3. So this is 3.14 into, how much is here? 3. So that becomes 4 minus 4 Henry. This is the solution. Okay, class. So you can note it down when you have written, when you are done with the writing part, just text me done. This completes your chapter EMI. Next week, we'll have the test of it. But test we'll see later. First, revise this lesson. Only short 3 topics are there. Just note it down.
Done, ma'am.
Okay, as you people are writing it down and have completed, you can leave. This was it about today. EMI is completed. We'll start with alternating current in the half an hour of the next class. Then we'll complete with the test. Please be prepared for the test. Okay. Thank you so much.
Thank you, ma'am. Allah Hafiz.
Yes, if you do the conversion, you have to convert everything. Since everything was given in centimeters, so that's why I didn't convert. If you are converting this into meter, then area also into meter square, n also number of turns per meter, everything into same unit.